Our next speaker, who's Courtney Paquette from McGill and Goldie Mine.
Great. So I want to thank the organizers for inviting me, so thank you. Also, please ask questions during this talk. I hope that I want people to learn things and understand. So please ask a lot of questions. So before we begin, I just also want to say that this has been sort of like a project that I've been doing for the last couple of years, maybe 3 or 4 years. Involves people from like Deep Mind, McGill, postdocs, grad students, etc. Okay, so what are some of the problems that we're facing in optimization and machine learning? And I would say one of the biggest problems that we see is that there is a gap between what is actually happening in theory and what is actually happening in practice. In practice, practitioners basically ignore everything that theoreticians say. I'm hoping there's not too many practitioners in the room, but it's basically true at this point. On the other hand, we can't really blame practitioners. And there's a reason from the theory side, which I sort of count myself as. What we do is we tend to produce plots which look like this. So these are runs of the algorithm, just different runs of the same algorithm on the same problem. And we're plotting suboptimality, and we always do better. Like we always put up our plots of ML and we say, hey, look, our results are always better than what our theory actually says. And I'm being very generous with my theory here. I'm actually putting it on the same scale, okay? In general, this is like not even on the same scale. And these are not to say that these worst case bounds are bad. They're actually attained. Okay, but somehow in ML, like we never see it and we're always somehow better. Okay, what I want to say from that is that maybe we should, instead of just saying, well, in practice, everything is much better, we should go back and actually say, why do we have that? Like, what is the reason that we always see things better? Okay. And what I want to argue with you guys today with, or maybe suggest something about it, is that one of the reasons why we see this sort of thing is that we probably have a mismatch with what our assumptions are. In optimization, we assume things like, well, they're just smooth, non-smooth, convex, non-convex, and that's how we break up our classes of functions. But maybe we need to go back and say, what is actually happening in these ML problems? Like, what are those assumptions? Do they actually hold? Okay. The other thing I want to point out is that often we're not super interested in convergence. Also, we're interested in other quantities. So there's stuff, I'm going to talk about that too. Okay. So what is the goal? Again, the goal is, can we actually bridge this gap between what is happening in theory and what is happening in practice? Okay. All right. So if there's anything you get out of this talk, I'm hoping it's this slide. Okay. So what is the idea here? What I want to do is I want to be able to predict at any iteration of SGD, of a stochastic algorithm, the exact loss function without ever running SGD. Okay? So that's exactly what's happening here. And I want to do it on a single run. And I want to do it with real data. Okay? So that's exactly what's happening here. Okay? You know, I can't do this in general, so I'm going to do this sort of for very simple functions, at least to start off with. What am I allowed to actually use about the data? I'm allowed to use the spectrum. So this is the spectrum with CFAR data. Okay. I'm allowed to use initializations, and I'm allowed to use targets. But again, what I want to do is at each iteration of the SGD algorithm, I want to be able to tell you exactly what that loss is without ever running it. And we can do that. So this is the plot of this. So what's happening here is your iterations. This is empirical risk, so I'm reusing data here. I'm doing an empirical risk minimization. A single run of this is just me doing CFAR data off of it. That's what the squiggly lines are. That's actually SGD. And my prediction is exactly this straight curve. Okay, I can predict it, even on a single run. Okay, again, in any iteration, I can tell you what that curve is without running it. Okay, first, any questions? Stop here. Everyone clear with the idea?
You're saying you're reusing data?
Yes, I'm reusing data. So I'm doing just like I'm choosing an index uniformly at random and updating. That's how I'm doing my stochastic. So I will eventually reuse all my data and repeat it. Any other? Starting off, see?
Oh,
Second
sorry, just a question. So what is the model that you are optimizing?
Yeah, so at the moment I'm going to do the least squares. I'm going to extend it a little bit. So this is actually a random features model. So I'm taking my data and I'm just hitting it with a random matrix, doing an activation function off of it, Rayleigh will work, and then minimizing just sort of the last layer on this one. Yeah. Any others? Okay, good. All right. The other thing I'm going to say is that my prediction is going to be like if SGD diverges, my prediction will also diverge. So they correspond. Okay? Yeah.
Do you have expectation somewhere in the formulation?
No.
Oh,
These are going to be last iterates, and they're going to hold with overwhelming probability.
I mean, the object function, you minimize the expectation of the
Yeah, so
square.
because this is a 2 norm, it's summing it all up. So yeah, it's doing an expectation.
Okay.
Yeah, into it in there. Yeah.
Okay,
yeah.
so okay.
I normalize my data. Sorry, I normalize this so it has like a 1/n behavior. Yeah. Good. See, I know I should stop on the second slide. Okay. The other thing I want to point out about this is that I'm an optimizer. I don't want to lose my job. This isn't really about being able to exactly predict this behavior. Doing these predictions is extremely costly, okay, as more costly than actually running the algorithm. The goal here, though, remember, is that we want to actually be able to see, here's what SGD does. So if I'm able to actually predict using data what SGD does, I can actually use that prediction to gain insights about the actual algorithm itself. How do we choose step sizes? Why our convergence are much better than we see? Okay, that's the ultimate goal, is that once you have this prediction, you can actually use it. Okay, all right. Slide 3. Okay, so now comes the question of, I started with, well, what are the typical assumptions that we should be making? So the idea here is that, in optimization, we're just minimizing some problem. But what is actually typical in a lot of the machine learning problems is that they're what are called high dimensional. That means that both the number of features, so the space for which you're minimizing over D, and the number of samples are also large simultaneously. Okay. So just to give you an understanding of that, what I'm actually going to assume is that the ratio of features to samples is actually growing both large simultaneously to some constant. Okay, so samples and features are growing. And if you actually plot this along state-of-the-art models, it's a little old now, data points versus parameters, and you did a polynomial fit, you would actually see a linear line. So like the real data sets and the real state-of-the-art models, they've been optimized for various other things, seem to follow this trajectory of saying data points and number of samples grow both large simultaneously. That's been the trend recently. Okay, so making this assumption is not so bad. Okay, so the goal here is that everything is large, high dimensional. So I am not going to be able to show these results hold when dimension is small. I'm not going to care about when solving the problem when dimension is 2, 5, 10, that's fine. I'm going to only be caring about when the dimension is like 1,000, 1,000,000, etc. That's the idea here. Okay, so what makes high dimensions very different? Well, you have more room, so you have more possibilities. That means inputs which you generate worst case complexity are very, very far from the typical one. This is like an average case idea. So just to give you an idea of how you actually see this, let's look at some ideas from high dimensions versus low dimensions. So here's a question for everyone. How many vectors can you find which are simultaneously almost orthogonal in D dimension? That is to say, if I look at X transpose Y, I want less than epsilon. That's what I mean by almost orthogonal. How many of those vectors occur in high dimensions? Guesses? So hopefully there's some probabilists out in the room. Or if you want to know the answer, it's exponential in D. Wow, that's a lie. Okay, we always think of orthogonality as being kind of special, but in high dimensions, it's not special. Alternatively, you probably have seen this from maybe a high dimensional class. This is the equivalent of this statement. If you fix a vector X on the sphere, you draw another vector Y uniformly from that sphere, then their inner product is almost always 1 over square root D. Okay, That means lots of things in high dimensions are almost orthogonal. Choose any fixed direction. What does that mean for us? Okay, let's go back to our problem. Okay, we're solving a loss minimization problem. We run SGD by choosing an index uniformly at random, and you generate a stochastic gradient. What that means, or what we usually think of, is we say, well, this holds an expectation to roughly be the loss, so let's treat this like gradient descent, right? But if we're in high dimensions, we actually don't have this little fact. Why? Because everything is almost orthogonal to each other. So this stochastic gradient has very, very little actually pointing in the direction of the full gradient. Most of it is actually orthogonal to it. We should use this. This is a weird fact. This is high dimensions. Okay? Clear? Yeah.
Are you assuming that are IAD or?
Yeah. The data is generated. You can think of it as the data is generated IID usually. They can have covariance in the feature side.
Yeah. So what are your assumptions on covariance then?
I'm just going to assume bound. I'll show you the setup in a second. Yeah. Great question. Okay. We'll see the exact setup. I won't be able to do it for everything. All right. So the question, though, is how do you actually capture high dimensional structure? So the way you think of it from an optimization viewpoint is that high dimensionality actually gives you some extra structure on your problem, and that you need to use it. Structure in the same sense of convexity, non-convexity, smoothness, non-smoothness, whether it's a finite sum. High dimensionality also does the same. But how do you actually capture it? So the way people generally do it is we're going to steal the ideas from statistical learning theory. There's some statistical learning theory people here. Some numerical linear algebra people have done this. Basically, the way you do it is you put a probability distribution on your inputs, which you'll show has some sort of universality property. So whether this is like law of large numbers, these are things like law of large numbers for like random matrices. Ideas here. Okay. All right. I'll also point out that some of these results will hold for deterministic designs. Matrices, so we'll see that at the end. Okay, so here comes the setup. All right, so I'm going to do a setup with something very simple to at least to start with. I think it can be extended and can have some fun. So here I'm actually doing the expectation, the expected risk minimization problem, where I'm minimizing over my data, and I'm going to assume that it looks like some expectation of F composed with A transpose X. So A here is my data. At the moment, I'm going to assume it's normal, mean 0, with a covariance. Okay, that covariance, I'm just going to assume is in operator norm bounded, independent of D. Okay. This X star is just the extra modeling parameters that you can have. You can think of it as like ground truth signal, etc. The main point here is that this little f, I'm going to assume is what is called pseudo-Lipschitz, and it sort of is low dimensional. So my data A is going to be high dimensional. The D is going to be high dimensional. So when I hit it with X, it's going to map it to sort of a low dimensional thing. So this F is somehow low dimensional. It's only the low dimensional thing. So in least squares, this would be the equivalent of the X squared part of it. Okay, not the inner product side. Yeah.
What is pseudo-Lipschitz?
Yeah, what is pseudo-Lipschitz? I brushed that under the rug. It just means that you still have Lipschitz, right? But you're also, it's not constant, so it's not like f of x minus f of y divided by x minus y. It's bounded by a constant. You can allow that constant to grow in x and y. So it's polynomial in x and y. So it gives you a little bit more freedom. It allows non-convex objectives. You don't, it's not just linear. Yeah. The thing it fails is sort of exponential stuff. Great question. Sorry, I snuck that in. Cool. Okay. So what does this allow? It allows you to do GLMs, multi-index models. So here, after you take the inner product, it's sort of low dimensional. M here would be your number of classes. This X star can represent a bunch of different things. It can represent ground truth signal, mean of data, some fixed vector. I'm just giving it some more modeling power in this. Okay. And what do you see? So let's look first at one pass SGD. So here I'm not reusing my data. So what the idea with one pass SGD is that you generate at each iteration a new data point, A and epsilon's the noise, and you update based off of that. Okay, so here I'm just plotting what that would be. And what you see, surprisingly, is that for large models, so where the D over N is growing, both are getting larger and larger. So the number of samples and the parameters are getting big, but going to some fixed constant, that you actually get concentration. That is to say, the entire risk evaluated at SGD is actually concentrating around a completely deterministic function. Okay? You can analyze this function, and it's completely determined by spectral properties of the covariance of that matrix. That's what you're seeing in this picture. So what I'm doing here is I'm running SGD iterations divided by D. Okay, so I'm rescaling time. I'm doing logistic, just doing KL. Okay, what I'm doing is that I'm generating a D is equal to 100 for a fixed N size, so the D over N is constant. Generating and running this and computing 10 different runs, and this the shaded region is the variance of those runs. Okay, and I'm going to increase each time. So now D is 400. Again, D over N will be constant, so I'm also increasing N. Okay, and you see that the variance across the runs is shrinking. And finally, it's shrinking all the way down so that you actually get a theory, which is just some curve, which is this red line. Okay. So there's a predictive curve. Okay. So why does this work? So why do you actually even see concentration? The first reason you see this is because there's a lot of extra averaging which is going on in the problem itself. So one of the places you have extra averaging is that you have this compositional structure of A transpose X. So A is very large, X hits it. This actually is averaging out in D. It's doing some sort of sum process going on. So that's why you sort of expect things. Now, the other thing which is kind of funny about this is that lots and lots of the statistics that we're interested in actually take some specific form. Why do we need this? If we actually want to predict the behavior, we need something which is like that we can evaluate things on. So if I form this W, which is where I concatenate X and X star, lots of your statistics that you're interested in are functions of what is W transpose Q of KW. Q here is some polynomial, okay? G is just some low-dimensional function. So lots of your functions can be represented as W transpose Q of KW. So if I write this out, it means that I have these four things here, okay? So examples of this are the risk itself, like all your distance to optimalities, the things that you measure, things for optimization and norms of gradients are all represented in this form. Okay? So everyone clear on this? So just to give you an example, because it's a little bit hard to see, let's just look at this. So let's look at least squares. It's the easiest to kind of start with. I can represent least squares as a trace, expectation over a trace. I do my expectation out. I get something which looks like X minus X star transpose K X minus X star. So you see X transpose KX. That's appearing. That is one of those things, those forms. Okay. Everything else also. X star transpose KX, that was also one of my forms. Okay. And the trace, the G would be the trace part of that function. It works for logistic regression. You can do exactly the same thing. Okay. Why does it work for logistic regression? It's a little bit harder to see, but the idea of why those statistics are appearing is because if you take A to be a normal, say, and you hit it with X, well, A transpose X has covariance X transpose KX. And it has, it has a, covariance, and the cross term between it has the X transpose KX star. So this is why these statistics are important overall, why they appear. So if you know this, then you can write this just in terms of these X transpose KX and X transpose KX stars and etc. You can also do little two-layer neural network things, again, for the same reason that this that this has the form of something that's just involving x transpose kx star, these will also. So what does this mean? It means that because most things that we're interested in have this very specific form, we only really need to understand the behavior of W transpose Q of KW. That's it. If we understand that, we just apply our low dimensional function to it and we get everything else from it. So all we need to understand is the dynamics of this property, of this function. Now, there's a slight problem with this. The problem with this is that you actually need to do it for every Q. Okay, it's actually a lot of Q's, every polynomial, and that actually turns out to be too big of a space. So there's net arguments, if you know some high dimensional probability stuff. And so this is problematic. So there's a fix to this that people know about. And one of the fixes is that instead of looking at this thing, we're going to look at something which involves something called the resolvent of a matrix. So we're going to form W transpose resolvent of KW. What is the resolvent? The resolvent of a matrix is where you take Z minus K inverse. And Z is just some element in the complex plane. Everyone okay with this? Any questions? Have I lost everyone with resolvents? Okay, so why is this useful? This useful is because this resolvent actually encodes everything about polynomials, actually encodes more. Why does it encode it? It encodes it via Cauchy's integral formula. So you can always represent W transpose Q of KW as a contour integral over the function Q of Z with the resolvent. So knowing the resolvent gives you everything about Q. It actually gives you more, gives you analytic functions. So now that's the idea. The idea is that as long as I can write down the formula for this behavior, which is like nice and compact, it has only a one parameter family with Z's, then I'd be able to represent all the dynamics of everything. And that's exactly what you can do. Okay, so before I do that, I need to introduce my time scaling. So in order to get the concentration to work, I'm going to rescale time. And the way I'm going to do it is by dimension. So if K is representing the iterates of SGD, that's the kth iterate of SGD, I'm going to represent that by T times D. So I'm going to discretize my time by dimension. Okay? T will be my continuous parameter, D will be my dimension. Okay? Everyone okay with that? Not step size, dimension. The important part here. And then you can prove exactly what you want. You can show that along the entire path, S of SGD will actually concentrate around a completely deterministic function. Okay? And because all of our statistics are of this form, we can recover that. We can recover information about this. And so we also get that any statistic that we're interested in of SGD is actually concentrating around a deterministic function. Oh, sorry, I went back. This deterministic function of S will be an ODE. So we can represent it by, okay, an ODE that's fully representing SGD. It's going to account for the noise that SGD creates. And the statistic you can just recover directly by doing this G and contour integral. Yeah.
Choose K proportionally because you're taking n proportionally.
Yeah. It has to do with time. So when the number of samples, because I'm not reusing samples in this case, I will reuse samples. But if you're not reusing samples, then you can only go out like number of samples. So time is like proportional to D, which is proportional to N. So, yeah.
Do you have any assumption about the noise, like the emission?
No. Yeah.
But you do assume that your sample is fixed, like your sample from a fixed set of data or something like this?
I will do that. This one is just a normal 0, but with any covariance structure.
Oh, it's a normal
with 0 with any
okay,
covariance. I will remove some of the normality.
Okay.
But the covariance, the way you do it is you can think of it, covariance can be whatever it wants to be.
Okay, I see.
Yeah.
Thank you.
Yeah. All right. I just also want to point out you get central limit theorems So it's actually, you're proving that the entire curve, the path, is actually a central limit there, concentrating from this result. Okay, how do you do it? Okay, I'm hoping to bring stochastic processes back again. Okay, so the idea behind this is we're going to create another process, continuous time process, which matches SGD, okay, in a special way. So the first thing I'm going to do is I'm going to do like continuous time process that we've seen before, but I'm not going to discretize with respect to step size. I want to make my step size large as possible. So what do I have to create my continuous time? As I mentioned before, I have dimension. So k iterates of SGD is going to correspond to t times the dimension. So that's how I'm creating my continuous time process. K over d is my continuous time. D is very, very large. That's why this will not work in dimension 2, but it will work in dimension 1,000, 1,000,000, etc. quite well. Then the second thing that I'm going to do is you traditionally do with stochastic process theory about stochastic approximation is you try to get your new stochastic process to have the same mean and covariance. That's the general approach. The problem with doing that is that this covariance of SGD is so complicated, you just can't work with it. It's just too hard. Even for least squares, it's too hard to work with. So what do you do instead? You steal another trick from SDE theory, which says that you can often average out or reduce the diffusion coefficient, reduce the problem with the covariance of SGD. Okay? And you decrease it by looking at dimension. So you simplify using dimensionality, using averaging technique to reduce this coefficient in front of the Brownian motion. Okay? It's called homogenization. It's a technique that's used throughout SDE theory. What do you still want to preserve? You still want to preserve that phi of this new process is roughly phi of SGD. So any statistic of it is preserved under. But you don't need to match mean and covariance. Okay? So what this means is that the iterate that I generate from this is not going to match the iterate of SGD, but any function of it is going to match it. Moreover, again, I can keep my step size as large as possible. So what this means is that if SGD diverges, this process will also diverge. That they match each other, okay? Because it's all dimension. And you can prove that indeed this is the high dimensional equivalent of SGD. That is to say, any statistic of SGD will concentrate around any statistic of this diffusion process. It's overwhelming probability. Okay. Any questions on this? But I lost everyone. So the main idea here is you can actually use this to find step size stuff. Yeah.
A statement.
Is that last statement uniform on phi, or you need to fix a statistic?
It's, well, okay. For any it's not uniform. For any, okay. The constant here will depend. There's a constant in front of this will depend on the statistic, and it depends on like the Lipschitz property of it. Cool. Any other questions? Okay, got a little bit of everything for everyone. All right, so how do you actually get deterministic equivalences? How do you actually get the deterministic function? Once you have this process, you just can do Ito calculus on it. So if you apply Ito calculus, because it's continuous, you just do calculus now, you get two terms. One, which is exactly representing gradient flow, same behavior. That's like the mean term. And the second term is the actual representation of SGD noise. This is actually what SGD noise does for that statistic. Okay. The other thing you get is an extra martingale term. Okay, that's because of the Brownian motion part. And so if you look at this, you might be like, okay, what is going on here? But actually, these two quantities can be represented as some function of that S matrix, plus the martingale, the dB, the Brownian motion term. Okay, so out of all of this, I didn't write it down. It actually turns out that all of these things can be represented through this statistic, this S. And so you might just play the same game and say, well, why don't I just let phi be s? Okay, so if I let phi be s, I get that ds is equal to g of s plus a martingale term, which you show is small in dimension, which will disappear in dimension. And so now you just say, well, I can just find the deterministic thing by just letting my deterministic thing be the solution to this ODE without the martingale. And that's all you do. So you can show that d of s is g of s. You can numerically solve that. And you also can play the same game with any phi and get it. So this will be the deterministic equivalent for these things. And that's exactly what you can show. You can show that phi under any statistic is equal to phi of that diffusion. Then phi of the diffusion will concentrate around that deterministic equivalent. Nice. And if any one of these processes diverges, the other diverges, if and only if. So they match up everywhere. Okay. And their concentration is pretty fast indeed. So by 1,000, you will see this. Of course, we don't care about solving these problems in dimension 2, so it's fine. So this goes back then to this question, well, that's kind of cool. You can solve these, but what do you gain from all of this? So one of these things you could ask is like, well, what is the choice of learning rate which decreases, say, a distance to optimality condition at each iteration of SGD? Well, you obviously cannot do that with SGD directly because of the stochasticity, but you could ask the same question of the deterministic function. Now it's completely deterministic. You can ask, well, when does the deterministic equivalent of the distance be a monotonically decreasing function? Okay? And so you can do that. So you can play the game. You know that I'm letting the script D be the deterministic equivalent of distance to optimality, say. You can write down what ODE it has to solve. It can be all represented by low dimensional things you can write. And you can optimize that and say, when does this thing be less than 0? That would mean I decrease at each iteration my distance to optimality. And you can write it down, what that is. So I just want to point out a few things. These A of S and these I of S, which appear in this formula, are always about little f, so they carry almost no information about K and D. Okay, they're completely low dimensional. They're like x squared. Okay, the low dimensional 1/2 x squared. Okay, so you can often lower bound these A and I just based on smoothness and convexity of f, little f, which is easier to compute. The other important thing that you see is that the average eigenvalue of your covariance naturally pops out of this expression. And so the point where you're seeing a decrease versus not a decrease is actually occurring at the average eigenvalue, not the largest eigenvalue. This naturally gives you your average eigenvalue appearing. In the case of least squares, just to put this all into perspective, the lower bound Q is actually just 2. And so you get this critical value of 2 over the average eigenvalue appearing. Exactly what you want. And you can prove directly that this thing diverges or converges at exactly that point, that step size, just directly from this analysis. Okay. You can also get convergence rates from this. So doing this, if you have little f, so this is not the full loss, but just the inner function is mu strongly convex and L Lipschitz, you can get a convergence rate, and the convergence rate now is not depending on the largest the condition numbers that we're used to. It's actually depending on the average condition number is what pops out, which is exactly what we've seen in practice. The average condition number is playing the more important role. It works. It's kind of fun. This is the best experiments in your life. These things actually just directly are on top of each other. You never have to do anything. So here I've played around with logistic regression. And what I'm doing is I'm just plotting the last iterate. So I'm running this for like x50 of SGD. Okay. And I'm plotting various different learning rates. And what I'm doing is I'm changing my covariance by fixing the average eigenvalue, the trace, but letting the largest eigenvalue grow, just to get a sense of it. And what you see is that they all sort of hit at this one point, where this is like where you stop decreasing, and it's exactly all the same value because I've averaged out the trace. I made the trace equal to 1 for all of them. This is actually working. Okay. You can do this with multi-pass now. So what do I mean by multi-pass? So I'm going to focus now on least squares because it's a little bit easier to work with. Oh, by the way, sorry, maybe I should stop. Are there any questions? Should pause here. Have I lost everyone? Everyone okay? Okay. You can do this for least squares, and you can do this for multi-pass now. So with the least squares, I'm explicitly putting the 1 over n, and my loss here is some sum over these guys. Okay. My A I'm going to view as having entries order 1. My B is entries also of order 1. Okay. And what does multi-pass do is now, instead of like generating a data point x, I'm generating, selecting an index uniformly at random. So that's where my randomness is coming from. Okay. And I'm updating my gradient just based off of that. So here I'm reusing my data. So I can go over and over and over again, my data. And what you see, again, is that for very large models, okay, as d over n both grow, okay, that the loss evaluated at SGD is going to concentrate around the loss of a deterministic function. It's completely determined by the spectrum of the Hessian, and you can write down a formula and analyze it. That's what you're seeing here. So now what I'm mapping on the denominator here is epochs. So when t is equal to 1, it's like going once through my data set. That's the same sort of scaling that I had before. And again, you see this concentration. If I generate randomly these A's and I do these curves, right, you see a variance which is decreasing as my dimensions get larger. Okay. You can also start to remove Gaussian assumptions. Okay, and have some fun. How do you do this? You can actually allow your model size to kind of grow, so you actually don't need the d over n constant. You can actually have it grow a little bit of polynomial. What is actually the key thing that is going on with these normality that you're actually really using at least in least squares in particular, is that you're actually using something called the delocalization of the eigenvectors. Okay, what does that mean? It means that your eigenvectors tend to be uniformly distributed on a sphere. Okay? The classic example of this is if you take entries of your matrix to be normally distributed, you form AA transpose, then they're done on the sphere. But this property actually turns out to be true for lots and lots of high-dimensional random matrices. Lots of random matrices, basically eigenvectors don't have that much information in it. Okay, that's the idea in high dimension. Most of the information is in the spectrum. Okay. You can check if something satisfies a delocalization property using ideas from random matrix theory. Okay. And just to give you a sense of what else actually satisfies this. So the way you think of these, by the way, is these are universality properties of large dimensional random matrices. They're like central limit theorems about eigenvalues, eigenvectors. All of this holds. So examples include sample covariance matrices. So provided that your data is independent, but you have any covariance on your feature side, it satisfies this. Random features also satisfies this. Lots and lots of things satisfy. And it turns out, under that assumption, you can actually prove, again, you construct a stochastic process, okay, which is given by this formula, right? So you do the whole homogenization effect. So the idea here is that instead of the expected, you just replace all the expectations, expected risks, with their empirical versions. And where you see covariance, you would replace it with the empirical covariance. That's it. It works. Okay, so you can do the same. And you again see that you do indeed have a deterministic equivalent, and that for functions of it, you get that phi of SGD will concentrate around this diffusion, and this diffusion will concentrate around a deterministic function. Now for deterministic design. So I just need my A and B to satisfy properties involving delocalization. Any questions? I lost everyone again. Yeah.
What radix?
Yeah. Okay. Okay. There's a reason. At the time, we were only trying to get this for the loss. It's true for things beyond. It's basically true for C3 functions. The C3-ness, weirdly, is because of Ito calculus. To do Ito calculus, you essentially need C3. Yeah.
You're still going.
You're still going through the resolvent to get this.
Exactly. Yeah. Yeah. You always have to do some form of a resolvent computation because of yeah, you do the resolvent now using the resolvent of the empirical A transpose. Right? Yeah. Cool. Any other?
What if you go back to the discrete dynamics? Do you still have this nice property, like the dependence on the condition numbers and so on?
Yeah, it exactly matches. Yeah,
Okay.
and it only gets better as dimension grows. So, and it basically, the concentration is so, because it's just a concentration in dimension, the concentration will hold at like 100 or like 1,000.
So if that is true, then is it possible that you don't resort to all these continuous dynamics tools? You can
Well, the
prove it
problem-
directly.
I mean, this is sort of discrete in some sense because I'm still keeping D's in there. So
Yeah.
it's not the asymptotic. It fails to start to hold when D is like 2 or 10 or things like that. Your bounds get they get bad. So it won't hold in those. But
Okay.
when D is large, you know that these two processes are just close. And so you can use one versus the other. Yeah. And where the discrete, it matches exactly the discrete stuff. It's really nice. You should discretize in dimension, not in step size. That's the key. Yeah.
This is just a clarification question. So there's
Yeah.
randomness in the data, right? A and B.
Yeah.
Are you
yeah.
assuming randomness in also how you select the indices for the SGD update?
At the moment, I'm just choosing them uniformly at random.
Okay.
Yeah. You can start to do it. It's much harder. So there's a natural question. It's much harder to understand the randomness that is generated when you like fix a permutation and run through it and compute the dynamics. Because it essentially the problems with these things is that the covariance over time of the iterates gets more and more complicated. It has a more and more complicated dependence on the data. That's the thing. Here, the covariance and the covariance over with a uniform really is actually quite simple over time. It looks like this after doing some averaging out. But if you have a different choice of like how you choose your indices, this gets more complicated. This is like the meat. This is like what that choosing an index uniformly at random produces.
So if you had a different strategy, then you want to have something as nice as ATA.
Potentially, yeah. It gets much worse. Yeah. That's a great question. What is that? I mean, if you just did it directly and said, I wanted to check the covariance of the iterates of SGD, even with this multi-path, we're using this index thing, like using this, choosing uniformly at random and index, that covariance of the iterates of SGD directly is awful. It's still awful. What it allows us to do this simplification is that you have to use high dimensions to reduce it. Some of those terms will disappear in the dimension. And there's averaging going on. And that averaging effect, like you have things which hit like A transpose X starts to appear. That's an average that you need to use to help you reduce the covariance term always. It's just a trick. I don't know if it's a trick. It's a way to simplify the process so that you can actually get information about it. Cool. Okay. Any others? Really lost. No. Okay. In the case of least squares, it actually simplifies even more. So instead of having to look at all those statistics, you just actually have to look at one statistic, which is the loss, and the loss will determine everything from it. And the loss actually solves something called the convolution Volterra equation. So the loss will have the deterministic part. So sorry, the loss of SGD will concentrate around the deterministic loss, and that loss will actually self-solve each other. So it solves it. So the deterministic loss is actually just equal to the gradient flow plus a term which is mixing, which this is what the loss is appearing again on. This here is actually what choosing uniformly at random an index does to SGD. This is what that is doing. It's exactly that. And it's exactly a convolution Volterra. If you've never done Volterra equation, they're in your classic intro ODE book. Go back. I teach ODEs, so now I make my students know it. It's in your ODE book. It was in renewal theory. It's been around for a long time. Everything about it is well known. Okay, you have things like kernels appearing. So the kernel is just all it is it involves just eigenvalues of your Hessian matrix, your empirical covariance. Okay, that's what this kernel thing here, and your forcing term is just the gradient flow. What's beautiful about this idea with convolution Volterra is that everything is known about it. We know exactly when it converges, when it diverges, etc. So because of this equivalence, we can just say, well, when this diverges, then we know SGD diverges. And in fact, if you use that, it involves kernel norm bound. Then, oh, sorry, this should be L. Sorry, switch notations, L here. You know that the deterministic is bounded if and only if SGD is bounded. And from the proofs of how, when do you know these things are bounded, from very classical ODE theory, you can actually generate the whole average trace 2 over the average eigenvalue pops out. It's exactly that. Okay. You just use ODE theory. Really ODE. Oops. Oh wow. Sorry. What else you can do is that the loss, it didn't matter what, like the function, I could have plugged in any function. Remember, it holds for any statistic of it. So now what you can do is you can run your X case using SGD on the training and evaluate and compute a deterministic equivalent for the risk, the actual expected risk, and plot the two. So that's what I'm doing here. I'm plotting the populating streaming, one pass, versus if I actually use multipath. Deterministically, I can know what SGD is going to do. And what you see here is that and if you had streaming, something like, say, you had n is equal to 2,000, so you only had 2,000 samples on the streaming, you would stop at that value. But on multipath, you would go down and go up. And so what you can actually do is exactly predict how much data when you start to, or like, how do I say this? You can actually predict when should you reuse data? Like when should you actually do a multipath versus streaming study? Because you have complete deterministic 2 ODE functions for it. You can exactly do that. I just want to point out, this really does work. You can't check these properties of delocalization, but you can just put in real data sets and totally predict everything. So this is with MNIST, you can predict the training, you can predict the expected risk. Totally predicted. Okay, they exactly match. You see weird things in step sizes. I'm going to run out of time, sorry. You can see the weird functions of step size behavior. So what you see in the step size is that there's a phase transition, and you can exactly plot it. What that means is that there's a choice of step size for which on one side of the step size, your convergence looks like gradient descent or looks like gradient flow. And on the other side is noise dominated. And you can exactly predict what that will look like. And it has a different form. And at this jump point, it's not smooth. Actually, a phase transition there. And here you see that. So you can see these for various step sizes. I'll just briefly mention this. You can also do this idea if you wanted to for mini batch and stuff like that. So here I'm doing the exact same formula, but now I'm going to allow the zeta to be my batch fraction. Okay. And I can do SGD multipath with momentum. Let's say I extended it so you can do it. You still have the same concentration results. your loss will concentrate around a deterministic function. This function is now discrete because of the mini batch behavior. The mini batch actually makes it a discrete, so instead of getting an integral, you get a sum here. But it has the same thing. You have the gradient. What you get is a loss, which is evaluated at sort of like gradient descent, full batch, and something which involves the kernel and repeated again. What's beautiful about this is you can analyze everything, and you can finally answer questions about stochastic momentum. You can exactly choose near optimal parameters because everything's deterministic now. You can always work with a deterministic function. Okay, so you can choose, and you know exactly the effect on from the mini batch. And the idea is that, again, the average average condition number will play a different role than the largest condition number. And what you can do is then you can start to ask questions about, well, mini batch sizes. So one of the things you might say is I'm going to define something called the implicit condition ratio, which is the average condition number over square root the classic one. And when you're in the large batch, which I'm saying is that my batch fraction is actually bigger than this value, SGD with momentum looks like deterministic full batch SGD with a full batch momentum, and you get a 1 over square root kappa rate. When you're under this value, you look like SGD. What this says, though something we've all known about, is that there's a saturation effect, which is that adding more and more to your batch eventually doesn't improve convergence. We can now quantify exactly when that occurs, is that this simple value, average condition number over square root. If your batch fraction is bigger than that, you're going to get full batch. If it's less, you're going to get SGD. Okay? So it exactly captures that behavior. All right? And it works. It really does work. You can plot different batch fractions. You can plot sort of the last iterate. And so as you increase your batch fraction, what these gray things are exactly the ICRs for these things on real data. And they're exactly predicting. You see you go down, and then all of a sudden you flatten out. This is a saturation effect. You don't improve anymore by adding more to your batch. And this thing is actually really doing a good job of predicting that. Good. And then I'll just end and say thank you. And here are all these papers, and there's lots of questions involving this. I didn't put any up here because there's just too many. So I'm happy to answer any more questions. So thank you.
Any more questions for Courtney?
Yeah, just to understand a bit better. So let's say that you can do the mini batch in like one step because it's, I don't know, parallel, right?
Mm-hmm.
So what is the setting of the mini, like what is the setting that I should set the batch size to have the best real-time performance, the fastest real-time convergence? Is it exactly that
Yeah,
point?
for momentum it is. Yeah.
Right.
So if you're doing, this is exactly where that occurs. Yeah.
I see.
Yeah.
Perfect.
That's
Thanks.
the other way of thinking of it. At least from a convergence point of view. So this is, yeah. So, you know, if you're optimizing over something else for your mini batch, it might not be. Like a compute might be different.
Oh yeah, I was saying like you have one,
Yeah. Yeah.
Thanks.
Cool. Yeah. So you may not be able to answer this, but like in dropping out that martingale, is this really just for dealing with Brownian noise? Is that like the only application, or if it was some other color of noise, can we also drop
It's not
out the
other
martingale?
color. It's for it's for all color noise. We're not really dropping out the martingale. Again, the idea is that you create two processes. So you're creating two processes, and whose mean and covariance are sort of the same.
Okay.
And one way and then that's actually all that survives in the high dimension. All the other extra terms, like anything other higher moments, will disappear when dimension gets large. Basically, that's the idea. So you're not really dropping out, and it's not really Brownian motion. It really is representing SGD noise. You're not assuming anything on the SGD noise. Yeah. Are we good?
Any other questions?
So how does, maybe I misinterpreted the result, but the fact that you can make progress proportional to 1 over square root, the average condition number, as opposed to the worst case, how does it not contradict those, the classic lower bounds that based on
Yeah.
Chebyshev polynomials that, 1 over root k is the best progress you can make, where kappa is like the worst case condition number?
Yeah. It's because when you're in, it goes back to high dimension. So when you're high dimensions and you have stochasticity, it goes back to this question here, actually. When you're in full batch, this is actually grad L. And it's like, I'm pointing in that one direction.
I see.
This stochastic is like, actually, most of your directions from your stochastic are orthogonal to the direction that you actually care about. They have nothing to do with the full gradient direction. That's important. That's why you get average stuff. Average eigenvalue starts to appear. That's basically what's happening.
Thanks.
Yeah. They really, you have to think of them as two, they're not the same. You cannot do full batch deterministic optimization. It has nothing to do with stochastic now. And high dimensions, high dimensional, it looks very different. Very, very different.
All right, so let's thank Courtney again.
Thanks.
And we'll take a break for lunch.